All right. So yeah, thanks for coming back. So let's make sure I've got the sorted. Cool. Come on, you stupid thing. There we go. Beautiful. All right. Let's start it over from the beginning. So what I want to do now that we've got the basics of like using the tables, maybe one thing to ask while I'm there we go, getting this back. Have people done sort of stuff with truth tables before? I know a number of people have like used them or things. So not that many. That's okay. The important thing, what I want you to be able to do, what I'm going to ask you to do on the midterm, right, is I'm going to ask you to be able to construct tables and then use the tables to test various semantic properties. So these semantic properties are going to be concepts, notions, that are very, very close to the ones we talked about in the first lecture. But importantly, instead of being defined in a very loose or nebulous sense of possible, we're going to define them in terms of a magic word. What do we think the magic word is going to be? I think somebody said it. It's going to be valuations. Valuations are going to be the thing that we're going to define all of these concepts in terms of. And the reason why is I've given you now a mechanical way to generate valuations, right? That's sort of, hey, write them T's and then double it and then double it and then double it. And a mechanical way to evaluate the complex sentences based on the valuations. So we now have machinery to test. We don't have to think about, we can just literally quickly plow through and test. Is this sentence one that's always true? Is this sentence one that could be true or could be false? These kinds of things. So we're going to define up a bunch of semantic notions that are parallel to the concepts we defined before, but they're going to be defined in terms of valuations. So here's our first pair of concepts. The first pair of concepts are the notions of a tautology and a contradiction. And we'll say a sentence in TFL is a tautology if and only if it's true in every valuation. So that is, in every valuation, our complex sentence is going to end up true. Now, the way that the table is going to look is that means the column under the main operator, is going to be nothing but T's. Because remember, each row, each one going across, is a valuation. The whole collection of them is an evaluation across all of logical space. So to show that it's true in every valuation, that would mean in every single row it's true. And the representation on the table is the column. On the flip side, a contradiction, a TFL sentence is a contradiction, if and only if it's false in every valuation. So here, the column under the main operator is going to be nothing but F's. So how do we test this sentence to see if it's a tautology or a contradiction? We build a table for it. We look at the column under the operator. If it's all T's, it's a tautology. If it's all F's, it's a contradiction. If it's a combination, what kind of sentence do we think it is? If it's a combination of T's and F's in the column, what kind of sentence is it going to be? Yeah, it's a contingent truth, right? It's contingent. There are circumstances where it's true, valuations where it's true, and valuations where it's false. We've already seen examples of both of these. Right here. Remember the one that we did right before the break. Okay. So if we take the column under the negation, what kind of sentence is this? Come back to your man, right? This sentence is a tautology. Right? It's a TFL sentence that's true in every valuation. But there's a close sentence. Take the one that doesn't have the negation in front, right? Suppose that negation wasn't there. If this negation wasn't there, what would that different sentence be? What kind of thing would it be? Yeah, but let's use the term we just defined. A contradiction, right? Now, the important thing to note, to go back a slide, all tautologies are necessary truths. Not all necessary truths are tautologies. Because some of the ways you could be necessarily true might be in virtue of the meaning of the constitutive sentences, not purely in terms of your truth functional form. So a tautology is a type of a necessary truth, but not the other way around. Not all necessary truths are tautologies. Same thing when contradictions and necessary falsehoods. All contradictions are necessarily false, but not all necessary falsehoods are contradictions in this sense. But when we're thinking of TFL, we're always looking for these. And the thing to remember is the magic words. These semantic notions are always going to be defined in terms of valuations. Okay, so we've got our tautologies, we've got our contradictions. The next kind of cluster of concepts, we can talk about tautological equivalence. And this is a property that holds between pairs of sentences. So we will say that two sentences A and B, two TFL sentences A and B, are tautologically equivalent if and only if they have the same truth value on every valuation. So what we mean by that is that if we look at the columns under our two sentences main operators, those columns are identical. Whenever one is a T, the other's a T. Whenever one is an F, the other's an F. In every valuation. So the columns match up. Note that they don't have to all be T's or all be F's, just that whenever they vary, they co-vary. So we can test this using our tables. Again, we build a table for multiple sentences, but using the same process. We look at the columns and see if they match. To give you an example, let's take two TFL sentences. What do these encode? Do we remember? What English sentence structure do these encode? They're the same, but do we remember what English sentence structure do these two encode? This is neither nor. These are the two ways to do neither nor. And we can show that they're the same, right? So we show how they're the same, and we write them together. We extract all the atoms. In this case, there's only two. We generate our table. We copy over, right? Then you build the next level up. So where would we look for our next level? What's the next step in filling out this table? Yeah. We could do negations. We could do this negation and this negation, right? So we could do this one. Cool. How do we fill out this column? Again, the negation works as a flipper. Whatever value goes in, it gives us the opposite. Bang. What can we do next? We can do the other negation. It's going to be the same thing. Whatever truth value goes in, we get the opposite out. Okay? Now we actually, right, we could jump over here and do this one. But let's go ahead and finish off this sentence, right? How would we fill in this conjunction? Where are the input values for this coming from? The two negations that we just filled in, right? The two negation columns, those are the ones where we're getting our input values. And so what's the conjunction here going to look like? So remember, the characteristic truth table for a conjunction, it's only happy, it only outputs true when both inputs are true. So we get false, 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 and true at the end. Okay? Cool. So one of our two sentences we finished. Now we go over to the other one. Right? What's the operator we're going to fill in first on the other one? The disjunction, right? The or. And what's the characteristic function for the or? Yeah. It's easy to please, right? As long as there's one positive coming in, it's going to output a positive. Right? So we're going to get true, 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 false. And now what's next? The negation, right? This negation. And where is the input value for the negation going to come from? The disjunction we just filled in. The disjunction we just filled in. So when we feed those into the flipper, cool. Now, if we want to show that these two sentences are tautologically equivalent, where are we going to look? So the conjunction's one of them. Where's the other one? The negation we just did. These two. These are the main operators from our two sentences. Two TFL sentences are tautologically equivalent if and only if they have the same truth value in all valuations. Put another way, if and only if the columns under their main operators are identical. If there's even one valuation where they differ in truth value, then they are not tautologically equivalent. So, what this means is that I can give you pairs of sentences, and using this, you can tell me whether they are or are not tautologically equivalent. That's cool. Now we can show whether sentences are the same or not, at least with regards to truth functionality. We can also test for consistency. So we can say that some sentences, A1 through AN, are jointly tautologically consistent if and only if there's some valuation where they're all true together. Might even just be one. On the flip side, we'll say that some sentences A1 through AN are jointly tautologically inconsistent if and only if there's no valuation where they're all true together. So, if we want to test this, if we want to test for this using our tables, here's what we're going to do. We put all of our sentences down, write them along the top. We extract all the relevant atoms. We generate our matrix of all relevant valuations. And we then see, is there even one valuation where all the sentences are true? If there's even one, they're jointly tautologically consistent. If there are none, then they're jointly tautologically inconsistent. This is exactly the same concept as joint consistency and joint inconsistency that we talked about before, but defined in terms of our magic notion. Distribution of truth values for atomic sentences, valuations. So, to give you an example, here are two sentences. Well, let's see. What are these? What property do these two sentences have? So we know that they're equivalent. Are they jointly tautologically consistent? Jointly tautologically inconsistent? Consistent, right? Because all we need to have is even one valuation, even one row going across where the truth value of their main operators is true. Which valuation does the job for us here? The last one. The last one. Because on this last valuation, this sentence is true, and this sentence is also true. Note, if we had more sentences, we could keep looking. All we need to do is find even one where all the sentences are true. Importantly, doesn't mean that we need to have T's at every single spot. All that really matters is the T or F that we have under that main operator. The rest of them, the other columns, are bookkeeping to help us make sure that we fill in the right T or F for that main column. So, this means I can also give you some sentences and ask for you to tell me, to go back a slide, whether these sentences are jointly tautologically consistent or inconsistent. You generate me a table, and you then show me that there is at least one valuation where they're all true, or that there are no such valuations. Cool? We'll do some of these in practice, right? This is obviously the stuff we're going to be doing in the tutorial, but it's useful to just start to see how we do this sort of stuff. Okay, so we know how to look for things being tautology or a contradiction. We know how to show things about tautological equivalence. We know how to show some sentences are jointly tautologically consistent or inconsistent, but the big one is still lurking. We want to test for validity. To get a run-up for validity, we're going to define a different notion. We're going to define tautological entailment. We'll say that some sentences A1 through AN tautologically entail the sentence C if, and only if, there's no valuation, the atomic sentences, which makes A1 through AN true and C false. So let's unpack that, right? The tautological entailment relation is going to hold if and only if there's no valuation, no way to assign truth values to the atoms, where A1 through AN is true and C is false. That should sound kind of familiar. There's no possible circumstance where the premises are true and the conclusion, yeah, exactly. It's the same notion defined in terms of valuations. But again, it's defined in terms of valuation, so it isn't strictly validity, but it's a TFL surrogate. It means that there's no valuation where premises are true and conclusions false. So we're going to symbolize tautological entailment with our double turnstile. This is just a way to say A1 through AN tautologically entails C. We can also write it this way. If this is true, it says there's no valuation where A1 through AN is true and C is false. It's worth noting there's no limit to the number of TFL sentences that can go on the left of the double turnstile. No limit going up and no limit going down, sort of. The lower limit, what do we think the lowest number of sentences we could have on the left is going to be? It's going to be 0. Yeah. We'll have very special sentences where that's going to be the case. We'll talk about them in the next slide, in fact. I want to express and make it very clear, the double turnstile is not a part of TFL. It is something for us to say a relationship holds between some sentences of TFL. It's a way for us to say, us, speaking English, or sort of extended English, to say, hey, there's no valuation where the stuff on the left is true and the sentence on the right is false. Using this double turnstile, we can say some other things in shorthand. We can say this, where we've got the double turnstile with nothing in front of it and a sentence. And this is a just shorthand, cute way to say that C is a tautology. It depends on nothing. On the flip side, we can also write this, the second one down, where we have a sentence, the double turnstile, and then nothing at all. This is a shorthand way to say that C is a contradiction. And again, we're using contradiction here in the way we defined it earlier, right? It means that there's no valuation where C is true. Now, the other fun thing, and this comes back to the question we had earlier. When we think about our double turnstile, the double turnstile holding tells us that there's a conditional that's a conditional that is a tautology. Jesus, yeah. The conditional that's a tautology is going to be one where we have the conjunction of the premises, conjunction of A1 through AN is our antecedent, and then C is our consequent. If tautological entailment relation holds there, that conditional is also a tautology, and vice versa. Why? Well, in both cases, what it's telling us is there's no valuation where all the stuff that's in the front is true and the thing at the end is false. That's what tautological entailment relation says. That's also what it would mean to say to have that conditional be a tautology. So we can express tautological entailment relations in TFL using this method. We use a conditional, and that happens to be a tautology. But it's often going to be more useful for us to stick with the double turnstile. Okay. So here's the big payoff. If A1 through AN tautologically entails C, then the argument A1 through AN, therefore C, is valid. And I should say that little 3 dot symbol is just a way to indicate that the next sentence is the conclusion. It's just the therefore symbol. So again, if A1 through AN tautologically entails C, then the corresponding argument, where A1 through AN are premises and C is the conclusion, is valid. Nothing about it being sound, but whenever entailment holds, validity follows. Now note that I've expressed this just as a conditional. This isn't an if and only if. This is just an if-then. And that's because validity is going to outstrip tautological entailment. There will be arguments that are valid where the premises do not tautologically entail the conclusion. And that's going to be because of the meaning of the relevant sentences. But this is our gateway. We know if there's a tautological entailment relation, the argument is in good form. So the cool thing is now we have a tool to test for validity. We can test arguments for validity. We take the argument, we symbolize it into TFL, we put it into our truth table, and we see, is there even one valuation where the premises are true and the conclusion's false? If there is no such valuation, tautological entailment relation holds, which means it's valid. If there's even one valuation where the premises are true and the conclusion's false, then we know at least that the entailment relation doesn't hold. We've got very good reasons to say the argument is going to be invalid. And it's certainly going to be at least invalid expressed in TFL. So this is how we can use truth tables to determine validity. And we can also show an argument's invalid by the same thing. Again, we come up with a valuation where the premises are true and the conclusion's false. So this is the real beauty of this system. I have given you now a formal tool, a mechanical tool, to test for surrogate notions like necessary truth, necessary falsehood, equivalency, joint inconsistency or consistency, and most importantly, validity. And all we got to do is know how to build those tables and read the stuff off of them. This is our beautiful sledgehammer. And the sledgehammer does a lot of work. And it's a really useful little thing to have. Now, before we go anywhere else, pause, ask, what questions do you have for me so far? We feel like we know how to build tables, or at least the idea. We're going to practice a bunch during the tutorial. But if I'm asking you to say, show that a sentence is a tautology using a table, do you understand what I'm asking you to do? Is the task clear? It's one thing whether you know how to do it. I want to at least know that you understand what I'm asking you to try and do. Otherwise, it ain't no fun. Okay. Now, the important thing is that everything we've said so far, you'll always be able to do. No matter what I ask you to do in the midterm or for homework or anything like this, if you give me a complete table, one with every single damn T and F or plus or minus filled in, your money. But I also want to tell you some ways that we might try and save time. So that's what we're going to wrap up on. Some stuff about shortcuts and partial tables. Now, I am never going to force you to use shortcuts or partial tables. But there will be plenty of questions where you are allowed to do so. So let's talk about these. Again, if the concept of the truth tables is already confusing, don't worry about what we're about to talk about. Don't try and take shortcuts before you know how to do it right. So, here's something very cool. When we're thinking about testing for these semantic properties, you'll note that a lot of times we can get by with just one valuation. For example, if we want to show that a sentence isn't a tautology, show that a sentence is not a tautology, we only need one valuation. What's that valuation got to do to prove that it's not a tautology? Yeah, it's got to be false, right? If we can come up with even one valuation where the sentence is false, we know it cannot be a tautology, because a tautology is true in every valuation. On the flip side, we only need one valuation to show that a sentence is not a contradiction. We come up with one where it's true. So this gives us a way to do a shortcut. If you have a sentence and you want to show me that it's not a tautology, you don't need to give me a full table. You just need to give me one line, one row. One row where the sentence comes out, depending on which one you're trying to show, either true or false. Do we see why? Right? Again, definition says, in every case. So if you have even one counterexample, it is not the case in every valuation. Same thing when we're thinking about equivalence. Tautological equivalence says they have the same truth value in every valuation. So if you have a pair of sentences to show that they are not equivalent, we can get away with just one valuation. What's that valuation going to do? To show that they're not equivalent, right? We come up with a valuation that makes one of the sentences true and the other one false. No, we don't care which way. Just we need to be able to show that there's even one case where they differ in truth value, then they ain't equal. If we want to show that some sentences are consistent, one valuation. Because all we need to do is to show that there's at least one case where they're all true. The really fun one, though, is our last two. And I'm going to loosely talk about these as basically the same. If we want to show that an argument is invalid, or that a tautological entailment relation does not hold, we only need one valuation. Because we only need to come up with the one situation where the premises are true and the conclusion's false. So this gives us a way where sometimes we'll be able to save some time. Instead of drawing out the full table, if you know the argument's invalid, you can just give me a valuation that makes premises true and conclusion false. Or if you know the sentence is not a tautology, you can just give me a valuation that makes the sentence false. So we have something like this. Here's a quick and dirty case. We've got two sentences, and we want to see if they're tautologically equivalent. Now, normally this would be a 16-row table, but I'm lazy. I don't do that. Instead, I'm going to think about it, see if I can come up with a valuation that makes the two sentences differ in truth value. That is, can we come up with an assignment of truth values in our matrix for this stuff over here, an assignment of truth values that's going to make one of these true and the other false? Well, we can work backwards. Let's try this. Can we think of a way to make the left-hand sentence false and the right-hand sentence true? What's an easy way to make our conjunction false? If they're both false, it would work. If one of them is false and the other is true, that would also work, right? Cool. So that's, again, all we need for conjunction is easy. One of them lets us down. Could be both, but even one of them lets us down. Yeah? How about our biconditional? What will we need for it to be true? Well, so that would be if it's false, right? If we want to make it true, we want them to have the same. Okay. So let's think. What's an easy way we could go here? Yeah, if we make A is true, well, if we make A true and everybody else false, what happens? If A is true, then we've got a T over here, and what's the disjunction going to be? It will be true. So then you'll have true and true. So that biconditional will be true. And as long as at least one of these two is false, differ. We can go even uglier. We can just keep working backwards. There's another one too. Right. Again, the thought process here, if you want to try and give a shortcut, you try and work in reverse. Start from a truth value you want for your top sentence and think about how you would distribute the atoms to get the truth value result that you want. To stress, I will never force you to do this. This is something you can do if you're comfortable with the truth tables and you feel like you can save time. There's never going to be anything wrong by just hammering out the complete table. And I'm not going to ask you one with like 6 atoms where you have to do fucking 80 different rows, right? I'm not going to do that. Okay. Well, we'll skip the joint consistency one. But again, do we see how we would go if we wanted to prove that these are consistent? So we'd try and find a case, work backwards from one where this one over here is true and this one's true. We could do that, no problem. The really useful one is, again, about validity. This is the thing I would like you to know how to do. When we're testing for validity, when we're testing an argument for validity, what we're really looking for are bad lines, threats. So a bad line is where the premises are true and the conclusions false. So we can save ourselves some time by throwing away non-threats. If you have a valuation, a row on the table, where the conclusion's true, you're done with it. It cannot be a threat. Because the threat is always one where the conclusion is false and the premises are true. Similarly, if you have a valuation where even one of the premises is false, you're done with it. It's not a threat. Because again, we're looking for ones where all premises are true and conclusions false. So this suggests a way that we can speed up evaluating arguments using tables. Let me give you an example. So here's a sample argument. Right? We've got two premises and we've got our conclusion. And I'll also give you a suggestion about how to write these down. Suggestion, you don't have to. But I would suggest you write your premises, you leave a space to make your matrix, and you also leave a space, make it very clear, this is the conclusion, these are the premises. Now, our next step for filling out the table, what would be the next step in filling out the table? Well, we got to do something before we do that. What's the step before that? Yeah. We got to get the matrix, right? We got to get all the valuations. So we got to do that first. So we do that. There you go. Easy peasy. Now, if we're doing this step by step by step, we copy and then fill in, right? And there's nothing wrong with that. There's nothing wrong with that. And there's enough time, I want to also be very clear, there is enough time in the midterm for you to be able to do that with every one of the truth tables I'll ask you to do. But it's worth conceptually seeing how we can shorthand here. So now, once we have our matrix, let's go through and just fill in the truth values for our conclusion. And the reason we're going to fill in the truth value for the conclusion is because anytime the conclusion's true, we can be done with that row. Because it's not a threat anymore. So, we can quickly fill in here, right? Now our negation's going to hit the flipper. And then we're going to fill in our disjunction. Okay. So now, here's the really nice thing. Every row where there's a T underneath that disjunction, we don't have to fill it in anymore. We're done with it. So the only rows that we need to pay attention to are those two. The sixth, I guess that's the fifth and the seventh one. Now again, do we see why? Because the only thing that could be a threat is a case where the conclusion's false. So everyone where the conclusion's true, done. Thanks for playing. Now the next step is we go through and we see on those two rows, is there any way on those valuations for even one of our premises to be false? So we can fill those in. And here we can help ourselves out by, again, trying to see, can we make one of the premises false? So we look at these ones. And we think about, say, the disjunction. If we look at the seventh valuation, what's the truth value for our disjunction going to be? On that seventh valuation, what's our disjunction? It's false, right? That's going to be an F because the input values are both false. So here's the cool thing. That seventh row, also gone now. It cannot be a threat anymore. So we don't even need to fill in what happens to it over here. We don't care. We've only got one box left that we need to test. And it's that one right there. Right? This is the only possible threat. So we look and see, right? Actually, I should say it's our negation here. If we look and see here, what's the truth value going to be? Well, we plug in our parts, hits the flipper. So, is this argument valid or invalid? Valid. It's valid. Because there are no valuations. There's no way to make the premises true and the conclusion false. Because every time the conclusion's false, at least one of our premises is false. So that's a nice thing, right? We could have filled in every single T and F or plus or minus or 0 or 1 or however you want. But as long as we're careful and we understand what we're testing for, we can get away with shorthands. Cool? Cool. So here's the first neatest thing. We're done with TFL, guys. Great job. You are now fluent in a new language. Took you 3 fucking weeks. How awesome are we? But of course, TFL is just our first stepping stone. TFL is an amazing tool. TFL is an amazing tool, but it is a limited tool. And what we're going to do next is start in on our second language, first order logic. I want to stress, please, 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 for the next week, please read the book. It's very important that for the next couple weeks, we start to read as well as listen to these, if you haven't already. Because the jump to FOL is a pretty big difficulty spike. Cool. All right. Thanks, guys. We'll see you in tutorials. Otherwise, have a lovely week.